Moez Jellouli from ISL Ingénierie. I will present you today an example of application of digital twins. So I choose to present you an example for hydraulic infrastructure monitoring, but you can have a lot of other examples. So the summary presentation. First, I will present.
Excuse me, Moez, just excuse me, we don't see the slide.
Then I will explain you the concept that I know that there is a different definition, so I will what is digital twins to us. Finally, I will present you an application of monitoring of the digital twins to the monitoring of
Moez, sorry, Moez, can you hear me? Jeremy?
So for the introduction, I will just present my company and myself. ISL Ingénierie is a French engineering company. It was created in the 1986. In this year, we reached about 135 collaborators, and we work on many activities, always in link with the hydraulic and the civil engineering. And we work in a lot of countries over the world and presented in many towns in France.
Excuse me?
So inside the ESL, there is a transverse simulation department. We call it SIM for Pole Simulation Numérique in French. And in this pole, we are about 30 engineers dedicated to simulation. I have the privilege to manage this department. And we make a lot of simulation, hydraulic, thermal, for civil engineering, mechanic, etc.
Oui, ne partagez pas le bon écran, on voit que le slide initial, on voit pas les autres slides.
Added to the tools of simulation engineers, and I will explain this today.
En fait, on voit pas du tout les slides, on voit rien du tout. Ok, ça marche.
Sorry, Jérémy.
Je crois que there's a problem with the connection here, so they don't see the slide. Okay, just sorry for always the same this hybrid stuff. Is it okay now?
Yes. I don't know if you hear us, but yes.
Yes, yes.
Yeah, perfect.
Okay.
Okay, sorry.
So I go to the concept of a digital twin. So to know what are the digital twins for us, I will do the objective of digital twins. So at the beginning of like the objective of this simulation, we have the reality that we want to touch with the sensors, with our eyes, with any things that can catch the reality. The first thing that we want to do as engineers is to understand what is the reality, to make our logs. Then we want to model it and to take our models to predict the situation that the infrastructure will have in its life. And finally, with our model, we will compare our prediction of the model in the future to the reality that we catch. And we have always at the end the same question: if the measures are coherent with the model, everything is okay. But if there is some deviation, what do we have to do? Do we have to update our model or to make alerts? So at the end, the sensors that we have put, etc., are here to alert if there is something wrong with the structure. So the digital twin is one of the tools that can help us to reach this objective. So the objective of digital twin is to make all these steps. So before going to digital, I want to show you what are the other tools that we have, so we can compare between the tools that we use today to do the same thing. The first tool is like statistical models. Statistical models, so we have our sensors with our measure, we'll follow them, and each year or each day or each month at each measure, we will compare our measure just statistically to our model. But this model don't have physics. It's drawbacks that it don't understand the physics of the problem, and finally, it's not easy to calculate. An example after this, it's not easy to extrapolate statistical model. So the other tool we have is numerical modeling. Numerical modeling. So we will try to make our model with geometry and physics. We will need some simplification because the reality is complex, and we will have to make some simplification. The drawback of this second method is that it needs higher power computing power, much more than statistical models, so which are analytical and immediate. And the second drawback is that calibration is not always easy, because when you have thousands of data, it's not easy to calibrate our model to all this data, specifically if you have made a lot of simplification. So each simplification will add the gap between our model and our reality. And finally, the other drawbacks need numerical modeling, like finite element modeling, needs special software and experts. It's not always easy to make this for every structure that we have. So somehow digital twins is between the two models. The digital twin will need data like statistical model, but it will add physics to our statistical model. On the other hand, if you have a numerical model, numerical model can be done without data. So we will add data and automatic calibration to our numerical model to make digital twin. So you can begin with statistical model and go to digital twin. You can begin with numerical model and go to digital twin, or you can begin with a digital twin directly with data and with physics. So here is an illustrative example. It's too simple, perhaps, compared to the reality, which just to explain. So when you have data sensor with one parameter, so the parameter can be temperature, that can be the water level at our reservoir, and we have a lot of data here for point, but in the reality there is thousands of. We will make our statistical model. I'm very happy because all the points consistent with our statistical model, everything is okay. And one day we have a deviation. The parameter is outside the bound of our statistical model. And you see here a little gap between the model and the point. So what is it okay or not? This is a question that an engineer will have. So because there is a gap, we will do let's say heavy finite element model. Heavy because it will take time, it will take computer power, etc. And finally, perhaps the conclusion that it is okay. So everything seems okay, but in reality, the problem is that we have this conclusion after 6 months. So the real prediction. And digital twin will make almost the same thing, but immediately. The power of digital twins for us. So back to the objectives. We need a simple tool that gives us precise prediction based on physics and also on data. This is for me the power of a digital twin. It has the physics and it has the data calibration. So of course we have difficulties, not always easy to make digital twins. And the difficulties is first complex to simplify. And so the second thing that with the reality we'll have knowledge to the question that, and we will some machine learning algorithm calibrate digital twin. So the ingredient to make a good digital twin, first is the precision with understanding of the physics, the simplicity, so we can use it in real time and like anywhere, ever in our mobile, and almost autonomous learning. So it's machine learning. Our digital twin can be automatically calibrated and used. So at the final, each digital twin must be updated to its purposes, and we have to make like for each problem and its constraints, we have to make special digital twin for this problem. So I will go to the monitoring. This is an example. I can show you other example, but here is an example. I hope that it will show you the power of digital twin. So in the case of hydraulic infrastructures, what are historic infrastructures? They are structure where with coupling with water. So we have dams, dikes, locks, etc. We have a lot of example hydraulic structures. And the difference is that water will affect the mechanical, the hydraulic, also the thermal behavior of our structure. And this is like a complex problem. If you want to make it with just statistical, it's not always easy. And with numerical, we will need a heavy model to model all this. Classically, so this is not the digital twin. We use monitoring with what we call HST models. So HST models are some addition of three terms, hydraulic, seasonal, time terms. This is widely monitoring hydraulic structures even today. The first limit of this HST model that are fully statistical. Even if it is seasonal, etc., we try to make some physics, but it's very simple physics. And of course, like I have said before, statistical models are hard to extrapolate to new situation. The second limit is not coupled model. So you see this is just a sum of three terms. There is no coupling between hydraulic, seasonal, and time. As an example, for example, the seasonal effect, we know that there is different from an empty reservoir or with a full reservoir of, for example, in the case of dam. And so we will try with our digital twin to correct these limits. So how we will build our digital twin? As input data, we will have the water level of our reservoir. We will have a daily average temperature, and we will have a rainfall. This is like input data. We have them with our knowledge of the environment. As output data, as sensors, we will have the displacement of the structure with pendulum or extensometers. We can have core pressures that we measure with piezometers, and also the leakages of our dam. So the first step will be just simplification of the reality, making analytical relation, but this analytical relation will not be as simple as HST model. It will be coupling, nonlinear effect, but at the end we have a function, can be a long function, but at the reality there is a function with parameters P1, P2, P3, etc. that are the calibration parameters, and as input data, this function, once it's calibrated, our digital twin, and it take water level, the temperature, and the rainfall as input parameter to have our outputs, so the displacement, etc. Once we have write this analytical question, we will need machine learning. So in the case of ESL, we use what we call it SPSA algorithm to calibrate the parameters. You can search on the internet about this algorithm, but its power is it can calibrate like any question, any analytical equation. but have some drawbacks. PSA algorithms are very powerful to calibrate complex equation. And our calibration is okay. We can deploy digital. At the end, it's just a Python or R library. So it's not a complex finite element model. It's just for people who know Python, just some lines of Python. And okay. So some tools, I want just to show you some examples of the tools that we use in our digital twins. One powerful tool is what we call them the convolution products. I don't know if you have already seen these convolution products before, but if we have like a function f, so f can be temperature or pressure or hydraulic water level, we can add delayed or diffusion phenomena with our convolution kernel or filter. Sometimes you find the term kernel. So making this in Python, it's already existing in Python, in R, etc. So it's just immediate. It's not a problem. And we define two types of kernels. Each kernel have one parameter. It's the time characteristic TC here. The first is used to calculate the mean temperature or the average temperature of a wall, for example. And the second term is to assess the temperature or the hydraulic or pressure at a given depth. So it have a delayed phenomena are present. Here is an example. So I take a simple example. You have a wall with external temperature at the both sides. But we can also use it if you have different temperature at each side. For example, if here I take the example, we have this 10 degrees in 30 days, and after this we stop the heating, and we calculate the temperature, the average temperature of the wall with a finite element model and with our digital twin. Just one line of Python. It's very easy. Once we understand it, it's very easy. And you see that we have almost exactly the same result immediately without any finite element model or something complicated. We tried also with sinusoidal variation of temperature, and we have always the same results with finite element and with digital twin. So this is a very simple digital twin. There is more complicated digital twins. And at the end, we take like a random temperature or a real temperature, and always have exactly the same result with finite element. So any variation of external temperature, we calculate immediately the average temperature of our wall. So this is interesting for calculating temperature, but it will be also interesting to calculate the, for example, the displacement of the wall, which will vary linearly with the average temperature of our structure. So we have used this our digital twin in the ICOL benchmark 2022. So the ICOL is the International Committee of Large Dams. It's an international committee, and each 2 or 3 years, perhaps 4 years, it organizes a benchmark. So they give a problem for researchers, for engineers, etc., and they give a question, and every team will try to have the best answer possible. And after this, there is a committee, and they compare the results of each team. In 2022, it was the problem was monitoring problem. So they give some data for a dam. We don't know which dam it is, but we have extensometer like this. They measure the distance between the point you have here. We have piezometers here. We measure the pore pressure in each piezometer. Also displacement with pendula here. We have packages, seepage, and we want to predict these measures. In reality, there is 12 years that have been given. There is our data for our digital twin, and we want to predict 5 years after this between 2013 and 2018. Here you have the calibration period, and after this, the prediction period. And you see here that there is special event in our prediction period, where it's like the point I have shown before. It's outside the bound of our calibration situation. So just for an example, I give you the digital twin for pendulum. You see, it's not very, very complicated. There's some equation. This time is the convolution product. And you see here at this graph that our digital twin, so the red line, is calibrating quite well to the measures. It's not bad. For prediction, I don't have the point, so I just show you the curve. And you see that this question, there is some coupling in this question. Here, for example, there is coupling term. Here, we show it here. And after machine learning, the machine learning calculates itself the coupling term. We give it just the form, the equation of the coupling term. But at the end, it have been drawn back the machine learning. And when it's 1, there is no coupling. And after this, with the water level, the coupling is more and more effective. So we do the same thing with piezometers, with all the data that we have. And you see that for this benchmark, there is like 22 models that have been used. And our digital twin finished in top 2 in the results we have. We don't have the details. But the digital twin with simple equation give very good prediction. You see that our team is the first one. Like we are always in green or yellow. Other teams are sometimes in red. You can see also perhaps at right the different kind of things that we can do to make to solve these equations. So we are classified as analytical because our digital twin is analytical, but some other teams tried machine learning, just machine learning like neural networks, or hybrid methods. It's like a mix of other methods. There is also some teams that tried the finite element models. And you see that finite element model, what are the behavior, don't always give the best results because there is some simplification in finite element. It's not always easy to calibrate our finite element model. Conclusions. Our conclusion for ESL, first, we think that digital twin, this concept is quite innovative. So we work on this since perhaps 5 or 6 years, quite new for simulation engineers. It's also an agile tool because we can modify it easily. It's not like finite element. We have a laws. We have to follow the laws. Here we can add our laws. We can it's more flexible tools, and it mixes machine learning and physical laws. So I think the power of digital twin, it adds the machine learning algorithm to our physics or to our statistical models. The second point is that this tool is especially helpful in operating phases when we have data. So at the beginning of a project, we don't have data. It's not easy to make a digital twin. So we can try to make a digital twin, but we have to create a data with finite element model or other thing. It's possible, but in operating phases, it's more powerful because we have a lot of data. And I think it's my thought. The digital twin will replace progressively, but not completely, the other method that I showed before, like statistical model and physical models. That's all. Thank you for your attention. If you have any question here, or I have the email, you can contact me.
Thank you, Moez. So we can start with some questions from the audience or online. Yes?
I will ask the question in English, I guess.
It's up to you. I can translate for our students.
What you are presenting is statistics, and the definition of digital twin is inject machine learning inside the physics law. Are you using a specific to create that, or are you everything? Are you creating with Python and R?
In our case, we use directly Python and R.
Okay.
So, don't know for other companies, but in our case, we tried Python and R. In Python R, there is already some libraries that help you in making a digital twin. So you don't have like in C or other thing to make all the question by hand. So it's quite easy to add a library or a digital twin with the Python already.
And do you think you will use in the future a specific software? If there is a software for that?
I know that the developer of a finite element model since 10 years are developing more and more digital twin in link with their software, ANSYS, etc. and so on. I think that all these simulation programs adding some tools, but the tools are like taking finite element model, creating data, and using machine learning or neural network to make simple models. So they're going from finite element model to digital twin. I know this exists already, but perhaps there is it exists also other kind of.
And why don't you use this software?
It's a different use of. Personally, I don't try them because, but we can. That's not. I think that in our case, digital twin is. We try to make something simple. So making finite element model, too good or simple, it's like making a heavy something to make something easier. But it's possible. I think it's possible. It's not.
Or maybe it's because you wanted to test the digital twin, see how it works, understand the worker using Python and R before making your choice in software. No?
I think that we tried something. It's going very well. It works, so it's okay. Other methods are also working, I think. But it's sure for me, it's using such methods takes more time and more computing power than method with just analytical question that an engineer can write.
Okay.
Thank you. Another question? Yes.
And why do you use digital twins for what client? Or what?
Them for different kind of clients, but especially for internal use. Sometimes we use them for optimization, for example. We want to try to find the best parameters to our model or to our product. And with the digital twin, we can make simple equation. With machine learning, we will find the best parameters to our monitoring. This is another example. No, we use for a lot of client with also problems for. I take an example of we want to try to find a simple equation to like model analysis. So we have a lot of model analysis results, and we take all the model results for a first period, what is the shape of the first period. We make digital twin, and with like a simple parameter, input parameter, the digital calculated the things that we want to calculate with a heavy finite element model. This is another example. But this example is especially dedicated for people who are the owners of the dams, EDF, etc. Other dams owner are interested on this digital.
Okay, I guess we have a question from Mathieu, if the network is okay.
Yeah, can you hear me?
Yes,
Yeah,
for now.
perfect. Thank you, Moez, for the lecture. As a big user of and a teacher in finite element methods, I guess I will have soon to find a new job. When I saw your results with the finite element models in the last slides, it was awful in comparison of what of the other methods. I was very surprised by that. Can you?
Example, and they're most perhaps more interesting, but I want to show you something that is very concrete. But there is a lot of example with very good prediction of digital twin compared to other very complicated methods. Even me in the beginning, it's just a research problem. I'm not sure that it will give very good results, but it gives very good results. And even now for like a 2D or 3D problem, it can give you with machine learning a map of I don't know flooding, etc. It can calculate itself such things.
And I was wondering because I know, like you said, for your finite element model, you do nonlinear analysis, which can be complex and time-consuming for a computer. So can you just give an order of magnitude of the, for one example, difference between finite element method and the machine learning method for the time consumance for the computer?
Heavy finite element model. First, we can't make all the complexity of the reality in our finite element model. This is absolutely true. So make all the important things, and more we put nonlinearity and coupling, etc. More our finite element model will be heavy and time consuming.
Yeah.
But the model for me it's 1 day, 2 days of calculation. For I don't know 1,000 of points in our curve, so it's very heavy, and just immediate. It's just the immediate results. So it's not. On other hands, our finite element model can modelize anything without data, but
yes.
Our digital need data.
Yeah.
This is the
thing. Yeah.
The digital twins.
And you need a lot of data for the digital twins, yeah, of course. Yeah, thank you.
We have another question from Pachi, please.
Hello, everyone. I am a student of the Masters of Digital Twin. I am Pachi Cartelli from Spain, and I would like to ask if, given the results that that digital twin had in the contest that you get in number 2, are you applying this digital twin to real assets, to real hydraulic assets there inside ESL?
The example I show you here is a real example of them. So I show you the benchmark for this. This benchmark is a real case. I think it's the one example. We have used them in 2 other examples of dams that we know very well. It works quite well. Here is sometimes our data, for example. It's always for multiple the level water level as just 1 meter for 10 years. So even our digital twin can't predict exactly what is happening, even if there is a physical loss behind it. If you have just 1 meter, you don't have the prediction for 10 meter below. It's hard. So you can add some finite element model to enrich your data and to make digital twin, which you have just to add some calculation of finite element to enrich your data. But this is also one case that we encounter in our use of digital twins. So in our case, I know that for me at least, there is 3 dams that we have used digital twins with good results at the end.
Okay, and are you going to
Thank you.
export?
We have another question online or in the room.
I think
maybe
Pachi,
opinion
as a
how it will change maintenance practices for dam owners, etc. For instance, you showed mostly about the mechanical behavior, but imagine if you couple that with drone campaigns taking pictures of like the photography of the state of the dam, detecting cracks, etc. Do you think that how it will impact the future?
So I know that the machine learning is already being used for cracks detection, etc. I don't know if it's exactly digital twin, but machine learning is always there is some algorithm that directly take the picture and it gives the detection of you have just to train it. You have to take some picture of cracks and it will find all the cracks on your dams. But I'm not sure it's exactly a digital twin. But digital twin, if I go back to digital twins, I think that will help the dam owners. We are not dam owners, we help the dam owners. They will help them, especially to avoid false alerts. In the case of today we use a lot of statistical models. And statistical models sometimes there's some deviation between the model and the model and the measures. And this is just because we are outside the bounds of our calibration of our statistical model. And digital twin, this can help to avoid this false prediction, this false alerts to dam owners.
I have another question.
Yes, please.
What you have presented as a digital twin in the presentation is the digital twin of mechanical behavior, not of the hydraulic structure itself.
What I show here is
the building itself, or is it the behavior of the pressure the temperature that the building will support?
This model, at the end, the sensor is displacement, but the displacement is depending on the temperature. It will depend, so the water level just load for our dam. I don't show the example of piezometer, for example. In this benchmark, we also predict piezometer, but it's the same methodology, and we can use it for piezometer. So piezometer measure the pore pressure in the foundation, and we use the same algorithm. It's not the same equation, but the same algorithm to make the same thing with the same results.
So it's more you are representing a behavior.
Yes, we are representing.
Not a table, a building.
It's a 3D geometry.
Oui.
I know that. We have a different kind of digital twins. I know that for some company, digital twin is a 3D model geometry with a representation of the sensor with it's like beam model.
Exactly.
This is not the digital twin I presented here, but perhaps in the future there will be the same thing.
I think what's interesting is that to be able to predict displacement, pore pressures, etc., you don't necessarily need a fancy 3D model, but just the relevant input data, measurements, and correct physics behavior. And what's really interesting is that you show that with only maybe 10 parameters that you can fit very well compared to, I think, other people in the benchmark that may have used deep neural networks with millions of parameters, but if you don't have the physics put inside, it's not necessarily easier to do. I guess.
I think that BIM, etc., is like we call it illustrative digital twin. You can find this term sometimes, illustrative digital twins. BIM models 3D geometry, but it will not have the physics really. It's not the understand of the behavior. It's the representation, sophisticated representation of the model, but it's another kind of digital.
I see.
I think we have a question. Network. Mathieu?
Yeah, I hear you. Yes. Yes, it's a big debate currently. Is a digital twin necessarily includes a BIM model or not, or a 3D model? Let's be general. And there is no conclusion yet about that. I was just wondering, Moez, really practical question. Who paid for the all the works you have done on the 3 dams? Is it like the owner of the dams, the public institution? I don't know. You maybe I don't know. Because it costs it must cost something. So I was wondering who paid for that.
Sorry, you just got cut from the very beginning. So if you can ask the question again.
Okay, I cannot just question a very practical question. Who paid for all that work for the 3 dams? Who paid the hours of work?
Until now, it's like a research program inside ESL.
Okay.
But I know that different companies and owners are trying digital twins. So we are convinced that it's very interesting. Perhaps sometimes we will be paid for use of digital twins.
Yeah, that's a good question to convince public institution owners and stakeholders to pay for that, but it's complicated to convince them.
In the case of dams, I think that things will begin progressively. So,
okay.
Yes. Okay. I just wanted to say that the benchmark, I think, is a very good idea to show what you can do either with what you cannot do with very complex models and what you can do with a more simple approach. And maybe it's not that expensive to put some money. It depends on what you want to predict.
Participate the benchmark. It took us like 4 days for all the sensors. Mm-hmm. So we have already the library of our digital twins, but it's very quick. If you want to make finite element for the same thing, you need at least 30 or 40 days to make model of displacement, of piezometer, of leakages, etc. And you will not be sure to have a good results.
Okay.